This is lecture 70 for Calculus 2 on improper integrals. An integral is called improper if either or both of the limits of integration is infinite, or if the function being integrated has an infinite discontinuity either at the limits of integration, or between the limits of integration. So when you go to solve these functions, you cannot just cavalierly go through and leave those infinities or those discontinuities in place. You have to take care of them. The way to do that is to replace the offending limit of integration, either because it's infinite or because it is at an infinite discontinuity of the function being integrated. You replace it with a variable. It says here. Then you evaluate the limit with that variable in place. After it's evaluated, you take the limit as the variable approaches either infinity or the vertical asymptote. And two things can happen. Either the result of the limit is a finite number, then we say that the improper integral converges. Otherwise, the improper integral is said to diverge. And the functions that I give here, the examples I give here, the functions will be positive. So we can talk about these integrals as the area beneath the curve. Of course, this isn't always necessarily true, but you can make adjustments later on that. Here's the first case of an improper integral. In this case, either the upper or the lower limit of integration is infinite. So here's just an example. It's the easiest way to see this. Let's say I'm integrating 1 over x squared, but I want to go from 0 to infinity. Well, this upper limit is infinite. I replace it by a variable. Here I used b. Then I carry out the integration, and after I carry out the integration, I take the limit as b approaches infinity. For this case, the integration using the variable b is arctangent of b minus 0. If I take the limit as b goes to infinity, the arctangent of b, the result is pi over 2. This integral then is said to converge, and it converges to pi over 2. This is a graph showing the function in red, and then the area under the curve in blue. That would be the definite integral from 0 to infinity. You might think it would be infinite, but in this case it is not. Here's an example of an improper integral that diverges. If you just think about this function and just kind of graphed it, you would agree that this is divergent. But sometimes the ones that look like they diverge, just on the basis that you're going to infinity, actually don't, as in the example that we did first. But here we have a decaying exponential. However, we're integrating from minus infinity to 0. So we replace this negative infinity with a variable, b, carry out the integration. This is the result of that integration is e to the minus b minus 1. Now take the limit as b goes to negative infinity. Obviously, e to the minus b approaches infinity itself as b goes to negative infinity. This is the limit, the result of taking the limit. So this improper integral is said to diverge. Of course, a graph of it just confirms that, although graphs aren't the way to evaluate integrals, you can see here, of course, that this area is going to infinity as x approaches minus infinity. Now we have the case when both limits of integration are infinite. In this case, we break the integral into two pieces before we start replacing those infinite limits with variables. I've broken it at 0. It's not necessary to break it at 0, but 0 is, of course, a very good number, since sometimes it simplifies results. All right, so I'm integrating from minus infinity to 0 here and 0 to infinity in the second. I replace the negative infinity with some variable b, and then I'm going to take the limit as b goes to minus infinity. I replace the upper limit of infinity here with the variable a, and then I'll carry out the integration, then take the limit as a goes to infinity. This is an even function, and the results are what you would expect for an even function. Remember, the integral from 0 to infinity of 1 over x squared was pi over 2. And here's the result of evaluating that first integral, where the lower limit of integration, which was minus infinity, is replaced by b. We carry this out again. We get the arctangent function Right? When we take the limit as b goes to minus infinity of the arctangent, we get minus pi over 2, but it's preceded by a negative sign. The result is pi over 2. From the first example in this lecture, the result from 0 to infinity was pi over 2, so the total area under this curve is pi, and this integral converges. And like I said, that's expected since this is an even function. Now let's look at the case of a infinite discontinuity or vertical asymptote at one of the limits of integration. So the function we'll integrate here is 1 over 1 x minus 1 to the 2/3 power. Obviously this has a vertical asymptote at x equal 1. So if one of the limits of integration, in this case the upper limit, is 1, then we replace that 1, the offending limit, by the variable. So now this looks very similar to the cases we did before, but now we take the limit as b approaches 1. All right, we carry out the integration. This is a result of integrating with that upper limit of b. Take the limit as b approaches 1 and we get 3. This integral converges. And now we have the fourth and the final case here, and this is a case where the vertical asymptote, or this infinite discontinuity, occurs between the limits of integration. You have to watch out for these kind of cases because it's tempting to just say, oh, just carry out the integration, there's no problem at 0 or 2. But the problem remains that at x equal 1 you have an infinite discontinuity. So what you do in this case is break the integral into two pieces, but break it now at that vertical asymptote of 1. Replace 1 with some variable b, and then take the limit as b approaches infinity, but from the left-hand side. Right. And now the other limit, the other integral, we have 1 replaced by a, but we're going to take this limit as a approaches 1 from the right-hand side. If you think of how you're integrating, see this is x, y, you're integrating from 0 to 2. You're going in this direction. So y, being this limit, you are approaching it from the left-hand side. Now here, when you're integrating this here, you're setting the a to be somewhat greater than 1, and you're letting a, taking the limit as it approaches from the right-hand side. So let's evaluate the second integral first. I'm going to take the limit from a to 2 of 1 over x minus 1. When I carry out this integration, I get the natural log of x minus 1. Evaluating at those limits, here's my answer. Of course, this first term is 0, but as a approaches 1, and it can approach it from the right-hand side, natural log approaches minus infinity. So this integral diverges. Now once you've broken into two integrals, if one of them diverges, the entire original integral diverges. You don't even have to look at the other one. But I just want to look at the other one briefly here. But even if that other the point is that even if the other integral converges, divergence dominates and wins. So it will diverge if one of them diverges. So here's the second integral, and note what the problem here is that I'm approaching this limit from the left-hand side. However, natural log function is not defined for values of x less than 0. So this limit is not defined. And now the point here also is that if you have this infinite discontinuity located between the limits of integration, there might be a chance that you will just blindly carry out this integration, and if you do, for example, if I integrate from 0 to 2, I get a finite answer of 0, and this is wrong. So you can get a finite answer, and that will be incorrect because this truly is an improper integral and needed to be broken at x equal 1 and evaluated.